Drag and drop the provided cab file onto the scstream preprocessor icon in the kicker. We often call this module stpre for short. Since this is a large model, it will take 30 seconds or so to open it in stpre. We'll jump ahead until this step is complete. In this model, all the analysis conditions have already been set and the meshing has also been completed. Here, we just need to add the output setting for the heat path file. This file type's extension is HPT. So, go to Wizard Condition Setting, Heat Path, and check Output Heat Path File. Then close the wizard and export the S file. We can then close stpre. Since we made changes, we should resave the cab file during this step. This will again take some time due to the size of the model. So we'll jump ahead to the end of the save operation. After the calculation is complete, we have the HPT file. Drag and drop it onto the HeatPathView icon in the kicker. We'll now call it HPV for short. HPV opens and we find there are three tabs called Part Temperature, Heat Balance and Heat Path. The key features of HPV are available on these three tabs, and we'll now take a look at them in detail. First of all, the Part Temperature tab presents the maximum, minimum and average temperatures of each part. For example, let's open the assembly folder of a battery module and navigate to its lowest part level. Here we can confirm the heat sources and check the max, min and average temperatures of individual parts. Or, if you close the assembly folder, you can check the temperatures for a group of parts. Please note that the part tree structure is managed by the XEMT file, which is exported at the same time as the S file. Next, the Heat Balance tab provides visual checks of the thermal balance for each part. That is, the components of received heat and released heat for each part. For example, looking at the pie chart of received heat for this group of battery cells, we can see that it is dominated by internal heat sources. The table and pie charts are also synchronized to the part tree. So, if you open the assembly folder of Battery Module Gap Filler, the displays will become more detailed, and you'll see that heat is mainly released to TIM, thermal interface material, resulting in a good heat balance in the table's in-out column. Lastly, let's move to the Heat Path tab, and note that we still have the battery cells group selected. This is a good time to explain the concept of a heat path. As a result of thermal analysis, the heat transfer can be thought of in a simplified string form. That is, you can think of a string or chain of thermally contacted parts that are connected one-dimensionally. The parts are like nodes, and heat passes between these nodes. This is the heat path. If we focus on one part on a heat path, it is in contact with other parts upstream and downstream. The upper T and lower T columns of the table show the average temperatures of the contacting surfaces, and the DT column shows the difference between them. That is, the temperature range within the focused part. The amount of heat transferred downstream from a part is shown in the heat transfer column. And the ratio of the heat transfer to the temperature range gives the thermal resistance, which is shown in the thermal R column. The data in the table is plotted on the graph on the right of this tab. The orange line shows part temperatures and the red bars are the thermal resistances. In this case, you can see that the second red bar is large, which indicates that the TIM has a high thermal resistance. The displayed length of a thermal path can be changed using a search number of part value, and you can switch the second or third most significant heat paths using a slider control next to order. Each thermal string is connected to other strings to form a huge network, and we will see next how to visualize that network. Click the Overall View button to display the network of heat paths. You can shift, pan and rotate this display in the usual way. This network diagram is also synchronized to the part tree. This means that even though most of the assembly folders are now closed, many nodes are still displayed. But we'll now introduce a technique to explore specific branches of interest. Firstly, by default, the network does not display fluid parts, but we can easily change this. Click Target Parts, find the coolant water in the list, and check its box. If you watch closely, you'll see how the displayed network then changes. In the part tree, now click the name of the coolant water while pressing down the Control key. The calc route function displays all routes which transfer heat between the two selected parts. That is, the routes between the battery cells group and the cooling water. Let's enter 20 watts in route threshold to further limit the display, and then click on calc route. Now only one route is displayed, and this shows that the heat from the battery module is transferred in one direction towards the cooling plate. So this is already an excellent thermal design. But as we saw on the heat balance tab previously, further improvement can be expected if the thermal resistance of a TIM can be reduced. So based on this finding, we can reconsider the thermal design. You can close HeatPathView now. Create a new folder and copy the cab file to it. Then open the cab file with stpre. We'll again jump ahead to the end of this step. We're going to edit the material property of TIM. Open the Parts Table dialog and enter Module Liquid Filler in Extract by Name. This is the common name used by the TIM parts. So when you click the Extract button, only the target TIM parts will be displayed. Their materials are set to TIM-C. Open the List of Materials dialog, check Editing Mode, and click on the TIM-C material. You can then increase the thermal conductivity to 4.4, which corresponds to the thermal conductive compound known as TC5022. Click the Set button to apply this change, and then close all the dialogues. Before exporting the S file, we need to remesh our model. This is necessary when the analysis conditions are changed significantly. Execute meshing by selecting Mesh, Meshing. Then export the S file and close stpre while resaving the cab file. Once more, I'm jumping ahead here through the more time-consuming steps. As we did before, run the solver with the new S file. If you don't have enough computational resources to run this simulation, you can use the files in the TC5022 folder that's included in the provided material. After the calculation is complete, open the new HPT file in HeatPathView. First, let's adjust the display to match what we saw in the previous section. Open the 5th battery module assembly and select the cell group. Also open the battery module gap filler assembly and set search number of parts to 4. You can adjust the range of the vertical axis of the graph by clicking on the maximum or minimum value and editing it. We'll change the maximum temperature to 27 to match our previous graph. If you compare these graphs, you'll see that the thermal resistance of a TIM has now dropped significantly. And as a result, the battery temperature has also dropped by about 0.4 degrees Celsius. So, to summarise, we have used HeatPathView to find the bottleneck in the heat path. We then reconsidered the thermal design and successfully achieved the desired improvements. This example and its workflow demonstrate Hexagon's thermal management solution.